Hi guys, in this video we would try and understand sp3 hybridization. Let us try and get into it.
This is what we are going to study, and would be good if you take pic of all these 3 pics that you are about to see for your reference.
Let's understand sp3 hybridization with help of methane as our example, CH4. So we need to understand a bit about carbon. Configuration of carbon is 1s2, 2s2, 2p2. This one corresponds to orbit number and this 2 also corresponds to orbit number, that is principal quantum number n. Now in first orbit it has got 2 electrons as I have shown here. In K shell it has got 2 electrons, right? In second orbit it has 4 electrons, that is 2s2 and 2p2. That is, so the second shell is L shell and it has got 2 electrons in s orbital or subshell and 2 electrons in p orbital or subshell. Alright, so that's about configuration, and that's what is represented over here. In ground state it has 1s 2 electrons, 2s 2 electrons and 2p 2 electrons. Let us understand a bit about elements. How are they referred in general? Now suppose X is an element. You have A over here, Z over here and N over here. A belongs to atomic weight, Z belongs to proton number and N belongs to neutron number. So these places are assigned for weight, atomic number and neutron number. Now let's come to carbon. As we are dealing with carbon, in case of carbon it's 12, its atomic weight is 12, atomic number is 6. Now when we talk in terms of atomic weight, it is neutron plus proton, whereas this is proton. So neutron plus proton, if you subtract proton from that, what you are left is neutron. So for this what we can say is A minus Z is equal to N. Alright, so this is in general, just I wanted to explain you something about how the elements are referred in general. Alright, okay, now let's get back to our topic, sp3 hybridization. Now what happens is, in ground state we have this configuration which I have already explained. Now this carbon atom gets excited. I need to explain over here that in case of hybridization, it is only the valence shell electrons which are involved. Valence shell electrons which are involved. What do you mean by valence shell electron? Valence shell electron means the outermost shell. Alright, in this case it is L shell. We are not concerned with inner shell, alright, or the K shell. Alright, so we won't be dealing with this. Alright, so these 2 electrons. So these 2 electrons would remain as it is. It's only the valence shell electron which would be involved in sp3 hybridization. So let's understand what happens to these valence shell electrons. Now there are 2 electrons over here. What we find in excited state, one of the electron jumps to this empty orbital. Alright, so we have got unpaired 4 electrons now. Alright, or rather we can say plus half spin, all having plus half spin. We know that p orbital are px, py, pz. So these are all singly filled orbitals. Alright, what I talked right now was about electrons shifting from here to this orbital and getting this sort of configuration. Alright, now let us try and understand about structure. What happens to this structure? Now these 4 orbitals, that is this 1s and these 3p orbitals, they remix, recast and remold to give 4 orbitals which are identical. Now which are identical in this sense? Now see, all the 4 orbitals are identical. Now what do I mean by identical? Now if we come back here, S we know is spherical in shape. This is dumbbell shaped. P orbitals are dumbbell shaped. If I talk of px, py, pz, those are dumbbells lying on x axis, y axis and z axis respectively. But after remixing, recasting and remolding, what we end up is, see, pear shaped orbitals. All four orbitals are identical. Their bond angles are also identical, that is 109 degree and 28 minutes. So now what we got is sp3 hybridized orbitals which are identical in all respect. All the four orbitals are identical and they are also having identical bond angles. Alright, so that's what I've mentioned over here. We call this as sp3 hybridized orbital because one of s and three of p orbitals are involved in this hybridization. Apart from that, the energy difference, if you check out initial energy difference, there's an energy gap between 2s and 2p orbital, whereas in case of sp3 hybridized orbital, there's no energy gap. All the four orbitals have equal energy, whereas here we found that 2s orbital had lower energy, whereas 2p orbitals had higher energy as per Aufbau's principle. Now, what we can do is we can proceed ahead. So this is already explained was electronic structure. Now explained its actual tetrahedral structure. So let us continue our process. So these are sp3 hybridized orbitals having one electron in each orbitals, and this is the structure as it looks, tetrahedral structure. Now what I have done is I filled up those one electron each in all the tetrahedral orbitals. Alright, now simultaneously we also need to understand hydrogen. Hydrogen has atomic weight 1 and it has got atomic number 1. So it has got one proton and no neutron. Alright, so this is how it appears. Now this is the electron cloud of 1s1. That 1 is obviously principal quantum number, that is 1, first orbit, and it has got one proton, no neutron. Alright, now another thing, that's one thing. Another thing that we need to understand is the number of electrons required for saturating a particular orbit. We are aware about the formula 2n square, where n stands for principal quantum number. Now in case of hydrogen, principal quantum number is 1. Alright, for the valence shell it's 1. So how many electrons would it hold? 1 square is 1, 2 into 1 is 2. So hydrogen requires just 2 electrons to complete its duplet and be satisfied. Whereas the situation with carbon is, let's understand. Now we had seen carbon structure over here. In case of carbon structure, it is the second orbit which is the valence shell. Let's understand how many electrons are required to satisfy carbon in its valence shell. Now as per the formula, it is 2n square. In case of carbon, n is 2, so 2 square is 4, 4 into 2 is 8. So carbon requires 8 electrons to satisfy its octet. Alright, so carbon, so hydrogen requires 2 electrons to satisfy its duplet, and carbon requires 8 electrons to satisfy its octet. Carbon already has got 4 electrons with it. Hydrogen has got 1 electron with it. So let's understand what happens. So the requirements are very satisfying. Hydrogen wanting just 1 electron to complete its duplet, and carbon wanting 4 more electrons to complete its octet. So s orbital, so hydrogen with its s orbital chases towards the sp3 hybridized orbital of carbon, each one chasing each sp3 hybridized orbital. So 4 hydrogen attacking like this, and this overlap is frontal overlap, sp3 s frontal overlap. So this is what happens ultimately. So hydrogen gets its duplet by sharing, the red one corresponding to hydrogen and the other one corresponding to carbon. So it's all frontal overlap. And so 1, 2, 3, 4, 5, 6, 7, 8 carbon satisfied with its octet, hydrogen satisfied with its duplet. Alright, via frontal overlap. Now why am I stressing on frontal overlap? The reason being, whenever there is a frontal overlap, it forms a very strong bond called sigma bond. Why strong? Because bond is surrounded by electron cloud. Alright, so there's all electron cloud surrounding the bond, sigma bond, so very strong. So this is the result of frontal overlap. So here comes the final result of sp3 hybridization. We have tetrahedral structure, bond angle 109 degree 28 minutes, and the bonds are sigma bond, 4 sigma bonds, and all 4 sigma bonds are identical, and the type of bond is sp3s, s of this and sp3 of carbon. So 4 sigma bond, 4 sp3 type of bond, bond angle 109 degree 28 minutes, and tetrahedral structure. How does the molecule look? This is the tetrahedral structure of methane, CH4, uniform from all the directions.
Okay guys, this was all about sp3 hybridization. See you again in sp2 hybridization video. Study well.